Okay, thank you. Since you missed the cool video of this 30-meter simulation, I just put it up because I really do love the way that you can see the full plume and such. So moving on to, and it went down quickly. There. Okay. Second talk today, we're going to be talking more about AI weather prediction, or what often gets referred to of AIWP. You've heard multiple talks about this before, some very specific systems. You'll get my point of view now, and also hear about NCAR's credit framework. And the thing we add is really prediction across various scales. So just as a reminder, we talked about post-processing, about machine learning parameterizations. We started the downscaling piece of the dynamic core, but today we're going to add to it the operator, the neural operator piece in addition. So I like to think that this work goes back to about 2018 when Peter Dubin and Peter Bauer of ECMWF published this first paper about it, where they about machine learning modeling, and at that point they were talking in terms of a toy model, a neural net with a neural operator, and they were comparing it to a T21 atmospheric model. And what they found at the time was not that it was better, but that it was competitive with models of that same very low resolution, and that there was hope that we would eventually get to the place where we would do machine learning forecasting. This is 2018. That's only 7 years ago. And, you know, I'm thinking about what I was doing 7 years ago. It's not that long ago. Okay, so after that, the next big example that I like to cite, and this is about the same time that the ERA 5 data became available and people started using it. And the first ones who really published a full global model was Dale Duran and his student Jonathan Wine. And their paper came out in 2021. I heard Dale talk about it at AMS back in January of 2021, and it really made a splash at AMS because it's the first time any of us had ever seen a full AIWP model. They used deep learning. They were focusing on the sub-seasonal ranges, looking at 6 weeks and at 4 weeks. And they were able to build ensembles. And they built 320 member ensembles in 3 minutes. Again, in 2021, this was very considerable. This is just 4 years ago, but they found similar scores in probability metrics for their 4-week and 5 to 6 week as the ECMWF S-to-S forecasts were getting. And again, made a big splash only 4 years ago. Hard to believe. Okay, after that, then we all know what happened. We started getting a proliferation of papers. By February 2022, NVIDIA posted an archive paper on ForecastNet. Not too long afterwards, Huawei unveiled Pangu Weather. Then Microsoft, together with UCLA, we heard about ClimateX this morning. And then by August 2023, GraphCast was published. That's primarily a Google product. We heard more about that earlier too. And then Privy Weather in September of 24. We heard more about that this morning. All this came very quickly in just a few-year process. Now, remember, earlier in the lecture, we were talking about identifying phenomena 2,000 years ago and using that to make forecasts. Computers being invented in around the late to mid 40s, but by 1950 we had computer chess, AI, coined in 1956. Then all of a sudden with GPUs, ERA 5 data, within 4 years we end up with all these AIWP models. What a huge acceleration we're seeing. Now, not too long after these started coming out, ECMWF saying, well, you know, Pengu weather, GraphCast, these all look good when they validate them themselves. What about if we validate them? So they, you know, published in a blog online in June 2023, a group of them showing that Pengu weather was competitive with IFS. And when they looked at, you know, even things like tropical cyclone track errors, you know, almost indistinguishable in terms of the error bars here. But they pointed out the scores can be optimized, machine learning models trained to do that, but they do tend to smooth out weather predictions and penalize forecasts of extremes. Now, we all know people have been working on that in the last couple years. ECMWF hired a whole host of machine learning scientists to work with their physical science scientists. They've been making very rapid progress, and they operationalized AIFS in February of 25. So this is all very, very recent. And of course, AIFS is very GraphCast-like. It's built on an encoder-decoder. So the encoder is attention-based graph neural network, processes the input data. You know, the processor itself implements a sliding window transformer. The decoder also does attention-based GNNs to generate the forecast. And it's designed specifically to handle the high-resolution input data and supports parallelism so it can be scalable. It's trained to produce 6-hour forecasts, as does their IFS system, and they often compare it to both their IFS and their high-res version. We did a bit of a comparison at NCAR. We have just a small internal one. Should we be looking at AIFS, and in particular for renewable energy variables in the US? So we are downloading the IFS data, trying to get it rather quickly. It's only been a couple months. They've had hub height wind, which is at 100 meters. But the IFS we're comparing to the high res at 9 kilometers, the ensemble mean at 18 kilometers, and then comparing to NOAA's global forecast system that's about, it's a quarter degree, so you know, it's from 25, 31 kilometers, and AIFS is at a quarter degree as well. And then NOAA-HER is our high resolution rapid refresh at 3 kilometers. So how does AIFS compare to those? And how are we going to compare them? So in the US, of course, we have a lot of observation systems. ASOS is the automated surface obs systems. That tends to be at airports, you know, looking at things like 2-meter temperature, dew point, 10-meter wind, visibility, et cetera. It's at very high temporal resolution, much faster than the models. It's maintained by NOAA. Okay, so here's a series of comparisons, and in all of these, GFS and NOAA's model is in orange. The HER short range is in purple. It only goes out to 48 hours, so it always cuts off. IFS in green and AIFS in blue. So, you know, is blue any better than the others? And indeed, in terms of RMSE, MAE, and mean bias error, it is better than the others. What was really surprising to us on these variables like 10-meter wind speed, the HER, that's high resolution, is low. And we were a little surprised and haven't really dug in yet to exactly why that's happening. And then blow up the short lead time. This goes from 0 to 400 hours. But if you look at the short lead times, the same is true. A little less easy to see on RMSE and MAE than in terms of the bias error. In terms of 2-meter temperature, bias error is, of the AIFS is more centered around the 0. And again, it's better in terms of MAE, RMSE. Blow it up so you can see the short range. And in this case, GFS does better at the short range. HER does quite well, as we would expect. And, in terms of bias error, but also in terms of MAE, RMSE, AIFS is on par with all the others. So we said, okay, that's nice. What about if in cases like in mountainous areas, how is it doing there? Is it getting the variability, the change, et cetera? So we looked at time series, and this is, just for some case studies at this point, in Denver, which is just east of the Rocky Mountains, as well as Copper Mountain, which is right up in the middle of the mountains. And what we see here is that this is where high resolution shines. The HER for the first 48 hours really does quite good. The black is the verifying, and you can't get that much variability. But the interesting thing about the AIFS is it's really missing the variability in these mountainous areas. So it does have some issues capturing the wind speed variability to the extent that we would like to see. So, what this so far we're finding, and again, this is at an early stage, that they show potential can outperform modern NWP models, on traditional metrics. They're very fast. The high resolution rapid rate refresh is still good for very short range and high resolution forecasts, especially where there's a lot of terrain. Need improvements on physical consistency, data assimilation, hybrid approaches might be helpful. And the AIFS, well, we're just going to compare the solar irradiance, but there's some issues with converting it to the same accumulated time frame as the other models show. Now, one thing about these models, and somebody else brought up this paper, does it really learn the dynamics? And, I considered this paper pretty seminal. Greg Hakem and one of his students, Masanamam, in September 2023, released this paper. And what they did was they took Pangu weather and wanted to see if it could learn the physics that is the basis of some of what we know. So they started with the model and they put in certain perturbations and initialized a tropical cyclone to see how it develops. And this is my favorite example that they did. They put in a perturbation in the Western Pacific, and as expected, it travels eastward, but it starts developing something, and by the time it's developed, gee whiz, that's a Rossby wave train. Now, it was never trained on Rossby wave trains. I did a similar problem using EOFs back when I was a postdoc a very long time ago and building stochastic methods. But in that case, we knew that it was based on EOFs, principal components, and we expected those principal components to have these types of responses like Rossby waves in. But Pangu weather has learned what a Rossby wave is, and it seems to be combining those Rossby waves in very smart ways to produce the accuracy in the forecasts that we've seen. Isn't that fascinating? Again, that's when I started thinking that, this has some promise. We are going somewhere. So Hakem concluded that the model encodes realistic physics in all experiments. It can be used as a tool for testing ideas before putting those ideas in our expensive physics-based models. I thought that was really interesting. Now, the other thing that happened just about a year ago, again, these things are happening very quickly, one a year. Can it be trained on observations? And this group of computer scientists working with physical scientists at ECMWF used their satellite data assimilation series and used that to train an AIWP model. And gee whiz, it's able to predict case studies of wind behavior over Europe. It's not perfect yet. They're just training on satellite data so far, reflectances, but it can infer winds from those reflectances. And they ended their paper by saying, our intention is to take our entire data assimilation framework, and again, they have the best data assimilation framework in the world, and use that to build AIWP models solely on observations. I mean, everybody's been arguing that, okay, the AIWP models are based on error 5. Everything is embedded in error 5. Now we're seeing we can do it on observations without that. Okay, so Greg Hakem with another student, Trent Vonage, recently has been looking at limits of predictability. Now, what were you taught in your classes on limits of predictability? Okay, when we've seen multiple plots on the improvement in predictability, that same plot with 3-day, 5-day, 7-day, 10-day. And, the 10-day is starting to be, beats climatology. And there's been lots of papers saying limits of predictability is about 2 weeks. We're converging on 2 weeks. Okay, what if you take GraphCast and you look at it over longer terms? And this is forecasts for 2020. The average error reduction at 10 days is 86%. Skill lasting beyond 30 days. Again, this is new. That demonstrates that given accurate initial conditions, skillful deterministic forecasts are consistently achievable far beyond 2 weeks, challenging that assumption that we've all been making. That's a limit of predictability. It's a limit of our models. Okay, what are some of the problems? And we've heard this from other speakers too. And this is from my colleague, David John Gagné, same one who did the Hill problem back when he was a postdoc with me. So we saw the rapid increase in number of models starting to even out, and skill starting to even out in around late 2024. The problem with most of these models, and basically all of them, is at some place they go unstable. And we heard in an earlier lecture about accumulation of error in time, and at some point, it just accumulates to the point where the model blows up. So how can we prevent that? Now, our physical models, we try to conserve, mass, energy, water vapor. What if we do that in a framework? So NCAR, led by David John Gagné, but working with his team, has in a 6-month period put out a series of papers. Of course, they've been working on this a couple years. They built a new community research Earth digital intelligence twin credit framework. First paper was first authored by John Schreck. The second paper came out in January 25, led by Kyle Shaw, using conservation schemes. Third paper, again led by Kyle. What if we use terrain following coordinates? Does that make a difference in precipitation forecasts? And then most recently, led by Will Chapman, he's the one with the atmospheric rivers, looking at Camulator, building a climate model in this same framework. Okay, so what is credit? Okay, it's an open foundational platform for developing and deploying AI weather and climate models. So so far they've been using data sets like ERA5, of course. Camulator is based on the community atmosphere model, a climate model, global forecast system, NOAA's operational model, and a CONUS 404 data set that we'll talk more about in a few minutes. And the models that are in it so far are WeatherFormer, that is NCAR built. AIWP model. They implemented Fuji, a Chinese model, and they're using a graph recurrent transformer for this mesoscale model we'll hear about in a few minutes. And the point is they're adding physics conservation, mass, energy, moisture budget. Okay, so here's the obligatory list of variables. They include, a land sea mask, integrated instantaneous solar irradiance at the top of the atmosphere. That can be calculated, so you might as well use that. That's going to help with the energy budget. And the different thing about this is on hybrid sigma levels. And we all know that most NWP models are on sigma, terrain following levels, and that helps us better model things like lifting over mountains, which then causes precipitation, et cetera. So that was the rationale that they used for doing it in hybrid sigma. Okay, so now they've done lots of metrics, comparing RMSE, getting worse in time, anomaly correlation, getting less in time. Now this, so weather former is the red and purple. IFS is the blue. Fuji, the original Fuji is yellow. Pangu is green. And then, we can see that it's right in there with it. So we're looking at weather former and Fuji, the yellow and the red, lowest in RMSE, and right in there, highest in anomaly correlation in terms of 500 hectopascal zonal wind, meridional, and air temperature, as well as specific humidity, geopotential height, 2-meter temperature. So it's doing really well, and in many cases beating the other models. It does have a nice kinetic energy spectra, in there with the others. And actually, there's a 1-hour version of weather former and a 6-hour version. And you can see that, they both are very stable and hold on to energy over the forecast period. Okay, what are these physics conservation schemes? And these slides I borrowed from Kyle Shaw, who actually put this into the credit framework. So the idea here is that we can correct the model outputs to conserve mass, energy, and moisture. So the idea is we have this non-negative correction so that, we're going to do this in terms of global dry air mass, global moisture budget, and total atmospheric energy. So for the moisture budget, we're going to focus on specific total water, and that is defined as a combination of specific humidity, cloud liquid water content, and rainwater content. For the energy conservation, we're going to look at fluxes at the top of the atmosphere and at the surface. So we need the flux forms of the precipitations, and those are accumulated every 6 hours. So this is an example for global dry air mass. So you do the initial forecast at t equals 0, you calculate what the global dry air mass is at the initial time. Go ahead, do your forecast, see what the new global dry air mass is, do a correction scheme to come out with a corrected forecast before moving on to T2. So the idea, okay, so for the dry air mass, it's integrate the integral of 1 minus the water content, okay, over the entire atmosphere. And it's added equally, or proportionally throughout the model. And so it's really just forcing that conservation. For specific total water, the idea is to look at the total amount of dry air mass, stay the same, and the dry air mass is constant. But here, the moisture budget, the precipitable water tendency, total precip and evaporation. Again, you can write an equation where the tendency of the moisture is evaporation plus precipitation. So you look at the total over the previous 6 hours, it's going to be balanced by the precipitation. And again, it's a hard correction after the first time step, making sure you do a global correction. Okay. Total atmospheric energy. In this case, the tendency is a sum of the sources and sinks. So, one writes a heat equation, includes phase changes, includes all kinds of forcings and sources and sinks that might occur. Make sure that you balance that equation, and again, do a hard correction after every time step. And just balancing by sources and sinks. Okay, so it's implemented in the credit framework. The evaluation is going to be in terms of Fuji base. That's without the corrections, and Fuji physics that does have the conservation schemes. Now, for this case, they did coarsen error to 1 degree, and the idea being they could fit it in our computer better so that they could test whether these conservation schemes work. So for verification, they're going to compare to 1/4 degree original error, trying to decide whether that coarsening was a problem or not. So that will be in blue, pre-processed error at 1 degree will be in gray, Fuji base in yellow, and physics in red. So the first thing that Kyle did was look at, is there a difference between the 1 degree coarsened error 5, using that to build the Fuji, or using the 1/4 degree, and basically found that for the variables he looked at, it really was pretty much a 1-to-1 match, and didn't really lose anything by using by using the 1 degree model. Okay, then this is a complicated figure. Let's start with the top left. Fuji base is the one that goes up and down. This is in terms of the global moisture budget, where without the physics, it varies quite a bit. With the physics, it's constant. We forced it to be constant. So the algorithm is basically working. Then we look at global precipitable water tendency. We want the tendency to be close to 0, and indeed for the physics, the tendency is much closer to 0 than for the base. Then global total precipitation amount. What we're seeing here is that for the base, it keeps increasing with time. You see a bit of a trend upward, versus with the physics, it does not. It stays centered at 0. Now, what about precipitation? For precipitation, they're looking at a stable, equitable error in probability space. Okay, this is a metric that quantifies general performance. It separates it separates conditions into dry, light precip, heavy precip. Most of the AI models have a drizzle bias, where they're putting out too much drizzle, which is why they're not getting the precipitation right. And what we're finding is the seeps, and this is the lower the better. For seeps, the Fuji physics is yet better. When we blow up on the end, we find that the physics is better than IFS. And the difference between the IFS seeps and the Fuji runs, again, we can see that the base has more negative. With the physics, it's closer to 0, as we're hoping. And that means that we can then model the precipitation extremes rather nicely. So why is the precipitation improved? Okay, so, and again, I mentioned that most AI models have this drizzle bias, and that the AI schemes tend to overestimate the drizzle. So let's stop for a moment and say goodbye to Dr. Adway. Thanks so much for configuring the workshop. Mm-hmm. Okay, but as we just saw, we had this trend upward in normal AI models, including the base without the conservation scheme. But because we force it to remain constant, and don't have that trend, it breaks the budget. So what's happening is, that as we run the model, we make the precip forecasts, overestimate drizzle, but then we correct it with the moisture scheme. That ratio is implied to the moisture budget, goes through the loss and goes back up to the top. So we basically, the correction has taken out those erroneous drizzle cases. So again, looking at RMSE for the IFS, Fuji base, Fuji physics, for various metrics, we're finding that in general, the physics is much better than the base, which is still better than the high resolution IFS in terms of RMSE. And the longer out, the more improvement it makes. So what we have learned from this is that what conservation schemes do, they do make the tendency more stable. The models do not accumulate moisture or energy anymore. It does reduce the drizzle bias. So we're getting better precipitation forecasts, and it improves the forecast of the prognostic variables, even those that aren't necessarily directly related to energy, moisture, or heat. And this is just a cool animation. Net thermal radiation doesn't change much in time, and very realistic precipitation for a particular case study that they did. So this is kind of the basis of WeatherFormer, the conservation. And then we're going to move into Camulator. And this was built primarily by Will Chapman. And all of these, of course, were a team effort. And it's, including John Schreck, Kyle Shaw, David John Gagnier, and a whole team of people doing some nice work at NCAR. Variables, a lot of climate variables. Again, this is trained on our climate atmospheric model, CAM, and it's over a 30-year observed record foresting, and it's just, again, at an early stage, but once trained, you can do 480 simulation years in a day. Compare that to the years that it takes to do ensemble runs for a full amount of climate model data. We can really learn by making big ensembles of climate. Okay, so the nice thing is, and again, it has the same conservation schemes as the Fuji physics, and it is stable out for hundreds of years, which is really hard to do. But because of the conservation, we get reasonable energy spectra. Total dry mass is conserved again. Moisture budget again conserved. Energy budget conserved. Total water, stays about the same. Energy tendency centered on 0. So the conservation schemes are working. It has very realistic teleconnection patterns. It's learned those teleconnections, even though they were not put in explicitly. When we look at ENSO, this plot is the ENSO precipitation, Nino minus Nina. Okay, so the CAM, simulated and for, I'm sorry, I don't know how many years, and camulator over the same, and gee whiz, we get the same pattern. So camulator is showing a lot of promise for being, a model that we can use to model the atmosphere over long time periods, saving a lot of computation time, being able to ask what if questions and answer them very quickly instead of having to wait to run climate models. So credit is open source, and it does provide a new pathway to customizing AI and weather modeling. David John likes to call it a new paradigm of AI ready processes. You need data. You can go here and check out the source code and see all those papers that I was putting out. The first paper is now in a journal, and the others will be seen going. They were initially in archive, but now being put into journals. Now, so this is all running our models at 1 degree, quarter degree, and that's what all these AIWP models are. But we know we want to do forecasts where we live, and we run our high resolution NWP models at convective level, 3-4 kilometers. Are we starting to see models at those levels? And indeed we are. The first one that I heard about was Warnon Forecast out of University of Oklahoma. This is an actual publication in JRL. They may have had an archive paper before March 2025. I heard a presentation by Dave Hall on NVIDIA's Stormcast. This past spring, they put out their archive paper in August of 2024. We are starting to see some realistic forecasts. Now, at NCAR, we're also, within the credit framework, developing mesoscale and microscale models. My colleague, Ethan Gutman, is leading the mesoscale effort. I'm leading the microscale effort. We recently hired Kyle Shaw, who did that conservation scheme, into our lab. He was a postdoc that was finishing and was looking for a job, and convinced him to stay at NCAR. So let's start at the mesoscale. So that is being trained from ERA 5. Well, the idea is to downscale from ERA 5 to something high resolution. Well, in the last couple years, NCAR worked with US Geological Survey to produce a 40-year high resolution at 4 kilometer simulation over the contiguous US, which we call CONUS. And with this, we call this the CONUS 404 data set. So it's 40 years of historical data initialized from ERA 5 using WRF to dynamically downscale, and then 40 years of future climate using pseudo-global warming, basically adding a temperature difference and letting it evolve. Okay, and Kyle is building the downscale in 3 domains: Pacific Northwest, Great Plains region in blue, and the Southeast. We're going to look primarily at the Great Plains area, which is the first thing he's tackling. Bringing in upper air data, some single level surface layer variables, diagnostic variables like precip, radar reflectivity, total cloud cover, et cetera. He's using elevation, accurate elevation at 4 kilometers, a land sea mask, land use, or a graphic variance, and then boundary condition, from 1,000 to 50 hectopascal, and then mean sea level pressure surface variables are being given from the training data. So he starts by downscaling, preparing the initialization. The idea is to convert ERA 5 downscale to CONUS 404, using a foundation model. Here you can see from each pressure level at ERA 5, you you have the static inputs, you have the downscaling, you bring in the high resolution data so that you can output, if you need to do any diagnostic variables from the prognostic ones, you can calculate them at that point. Okay, in terms of RMSE, again, very stable over a long time period, 2-meter temperature, 10-meter U and V components of wind, what he calls T4, that's an 850 hectopascal temperature. So we're finding that this is very stable. See if I can run this simulation. This is a case day of a frontal cyclone. The input ERA data is on the right. The target CONUS 404 is the middle. The AI model is the left. And you see that even though the ERA is changing very coarsely in time and space, the AI model is able to capture the same type of behavior that you expect from the CONUS 404, even in the case of a frontal passage over this region. Okay, same case. In this, here we're looking at humidity and precip variables, total precip, precipitable water, and 870 Pascal humidity and wind on the bottom. Again, ERA 5, very coarse, not very accurate, but the AI model has learned a lot of the behavior we expect. We're getting a few anomalous gravity waves developing here, and it isn't perfect on how the winds are matching the 404 winds, but it is doing a lot better. You're getting a lot better information than you are from the coarse ERA 5 model. Okay, now, my favorite part, the microscale model. When I was doing this project on connecting the mesoscale to the microscale, as I mentioned in my first lecture, I thought that, wow, we could be doing this with machine learning. Now, we need target data at high resolution. In this case, we're running NCAR's fast-steady GPU-enabled LES code. And you can see, even in the case like this, where there is a front comes through, changes in this urban, this is Dallas-Fort Worth area. Even for a frontal passage, fast-steady gets all the details really beautifully. This model is run at 5 meters resolution. Okay, so we're going to start by doing a downscale, then add a neural operator. So, as we talked about earlier, we found that we'd started with a GAN, a generative adversarial network, the enhanced super resolution version, ESR GAN. And although we could get good results doing 2 steps, it was really hard to use. And we heard that from the same experience from Elena Tomasi yesterday. And that led us to move to the diffusion model. We can go down 32 times in a single step. And it's working well on this fast-steady data. Now, what is our training data? Fast-steady was run for the noon hour for an entire month over the Dallas-Fort Worth. And as you can see here, bunches of different wind directions and cases and a lot of experimentation. Now, they didn't save all 30 days, unfortunately, so we're starting out with 13 days. Now, so we coarsen it like we did before, and the key is to include the high resolution building data in terms of terrain. It's gently rolling in Dallas-Fort Worth. So, we're using as terrain height plus building height as our lower level forcing to produce high res. And I'm just going to show you some initial simulations. We spent a long time on the GAN before we more recently moved to the diffusion model. Low resolution, you don't see a whole lot of structure at all. High resolution training, data. This is the target, and the model is able to generate it. Now, unfortunately, it's not quite on the same color scale, so you kind of have to mentally adjust. This is work in progress. Same true for the V wind component. W was also showing quite well, as long as you don't look too hard at the color scheme. Okay, so where does this lead us? We have our AIWP models, that we've seen are very successful at the global scales. We are starting to see mesoscale models, being trained over more mesoscales, convective scales, where we're able to model clouds, see some of the processes better. And we're just starting, I didn't show you a neural operator because we aren't there yet. We're just starting to get to the place where we can talk about then downscaling to the micro scale. So I think we're on the verge of being able to create generalized digital twins of the atmosphere at all these scales, yet to be seen whether we can really connect them the way my model does. But won't it be wonderful if we can run a coarse resolution model many times on ensemble runs using AI, downscale, run the mesoscale models, downscale again, and see what the eddies are going to be in urban regions, how it's going to transport air pollution, all the impacts that come to humans here at these micro scales. So we're getting there. Thank you. And wow, I went over. I'm sorry.
Questions? Maybe I can start with one. This credit you said is open source.
Right.
So for somebody uninitiated like me, how much of a learning curve is it?
Okay, so you can go pick up credit and start using it, but to try to train your own data on it, I think is going to be a little heavier lift. That's where students who attend courses like this, who spend time, studying machine learning, that's why they're here. They're being trained to be able to download these, train it on new data, and be able to make the next steps.
Okay. Yeah, I hope to use it.
Mm-hmm.
More questions?
You were saying AI models, saying that regarding conservation, said there is a good progress on the conservation. Can you elaborate more on it? I think it was too fast. I saw the energy budgets, and I also saw some conservation comments, but can you elaborate?
Yeah. Okay. The conservation method is actually amazingly simple. Okay. Time zero, you calculate total dry air mass, total liquid, total water content, the specific water content, and total energy. Okay. Go forward one time step. You look at how different it is, and you add that difference back into the model. Now, right now, it's done just equally around the globe, okay, at every level. Appropriately on levels, put it that way. So it's a very simplistic scheme. One can imagine coming up with more complex schemes in the future, but this conserving energy, as we saw, made a big difference, conserving all those quantities.
And you do this correction to all the stratas or just only on the surface?
No, it's throughout the whole depth of the atmosphere. Yeah, appropriately on each level.
More questions? Since there's time, maybe I can ask another one. So these Rossby waves that this thing picked up, it's amazing.
Yes.
So normally, I mean, people like me keep hearing that AI can do interpolation very well, but extrapolation, no. But this is something like it's extrapolating, right?
It is. I don't know whether I'd say it's extrapolating. It has learned the patterns.
Right.
Okay.
You can see that pattern.
It never saw that pattern before. And I think when they say that it doesn't extrapolate well, if you have a record of extreme events, for instance, and even if you oversample to try to train for those extreme events, you probably are not going to get extremes beyond what it has been trained on. Okay, but what we're seeing in these types of models is they're learning the physics, perhaps as we do the right types of perturbations, it will combine the physics in smart ways. I like to think of it as, at least my picture, and this may or not be realistic, is it's basically found the principal components of the system. And it knows how to balance those principal components according to the forcing at this particular time. So it finds the right combination that makes those modes of the atmosphere that we see.
Got it. Yeah,
Mhm.
amazing.
Ashley. I don't know. I'm having a hard time.
So I'm really intrigued by results that suggest that AI-based models can reduce the error growth rate compared to NWP, because they're not using higher precision arithmetic.
No.
So what is it, especially in the context of initial value problems? So what do you think is going on? Are they learning the attractor and shadowing nearby trajectories, computing averages of shadowed nearby trajectories, given that they're not really using higher precision arithmetic?
Yeah, okay. Yeah, so, the weather models, like any weather model, it depends on the initial and boundary conditions as you integrate out. And now we're seeing, as you conserve energy, mass, and latent heat, you're getting that very similar to the weather models, and in fact, better. Now, when we talk about cumulator that you run out 100 years, you don't get the weather at the right times in the way you would expect. You get, it's the same as any climate model. You get the right statistics, the right trends, all the types of forcings that you would see, but not this right pattern at the right time. We don't know what that's going to be in 100 years. So it depends on your time scale, I think, is the answer. Mm-hmm.
I just had a question regarding that energy spectrum that you showed. So in the initial plots that you had showed, you saw that spectral bias like we had seen in Ashish's talk as well. But in the later figures that you showed, I did not see that bias in the higher wave number region. So I'm just wondering what happened there.
Okay, and that's where I'm surmising, because I didn't actually do the calculation myself, but I think what they're doing here is plotting the spectrum over the relevant scales. So it may have cut off those very fine scales. The other thing is, by energy conservation, that tends to smooth the tail end of a spectrum too. So you're not going to get that energy accumulation at, normally, we think about, the energy spectrum and the dissipative scale. We get to the point where everything is at the very small scales, and then it's dissipated as heat. But, the model doesn't allow that, so it just accumulates it at the small scales. But if you cut it off or conserve, then you're basically taking that would have been dissipated and putting it back throughout the spectrum.
We had an amazing 2 lectures from Dr. Haupt, so let's thank her for that.
Thank you. Mm-hmm.